All right. Hi, everybody. Thank you for joining this Edit seminar. So today our guest speaker is Amar. He's right now in Dublin. So he volunteered to give this talk on his work on I interact. Right? So that is more like as I understand, a augmented reality approach that allows the users and designers to interact in additive manufacturing and designing. So it is allowing people to interact throughout the design and fabrication process, as I understand. So let's see the talk. Thank you, Amma. Yeah, you can go ahead.
Thank you, Trish. Good afternoon. I hope everyone is safe and healthy. Today I'm going to talk about a cyber physical system named I-nteract, designed for additive manufacturing. The system has been developed at IFOM, an advanced manufacturing research center based in University College Dublin. I am Amar Malik. I am researcher in cyber physical systems at IFOM and PhD candidate at University College Dublin. The other members are Dr. Hugo Lechmy, Associate Professor at Centrale Supélec France, and Dr. Robert Charlton, Professor of Cyber Physical Systems at the Dyson School of Design Engineering, Imperial College London. What are cyber physical systems? Cyber physical systems are integration of computation, networking, and physical processes. These systems include combination of several systems of different nature with main purpose to control a physical process. For example, for our system, I-nteract, the physical process that we want to control or improve is additive manufacturing. So what is additive manufacturing? Commonly known as 3D printing, additive manufacturing refers to the process of depositing successive thin layers of materials upon each other in precise geometric shapes based on 3D model files to manufacture three-dimensional physical object. There are 7 main types of additive manufacturing technologies. The one shown in the slide is called fused filament fabrication. The additive manufacturing process starts with the design of a 3D model either in a CAD software or obtained from a 3D scanning machine. The 3D model in the STL file format is sliced into layer and is converted into a specific instructions called G-code for the 3D printer using a slicing software. Then the 3D printer executes the instructions to build the physical object layer upon layer. Finally, the post-processing is done either to remove the support structures or to give the finishing touch to the 3D printed product. Additive manufacturing offers possibilities to not only print bespoke products, but also the possibility of enabling highly disruptive new business models. The business models that are based around the inclusion of consumers within the product design process. In spite of its huge potential, there are challenges in enabling the widespread adoption of the 3D printing. The outcome of the 3D printing process is a physical object existing in the physical world. In contrast, the 3D model used to print the object only exists in the virtual world, making it more difficult and less intuitive to appreciate the manner in which one can interact with it before printing. Most existing CAD software requires a strong technical background and is not readily accessible to a large non-technical audience, and does not solve the inherent difficulty of testing human-machine interactions for manufacturing. It is generally difficult for the inexperienced user to correctly locate and place objects in a three-dimensional environment while only having access to a 2D window into the 3D space through a computer screen. Furthermore, the use of traditional mouse and keyboard are unintuitive for the user and provide limited methods of interaction for assembling, creating, interacting, modifying, positioning, and shaping the 3D models within a three-dimensional environment. There are mainly 3 objectives to design I-nteract. Considering the time constraint, I know I'm going only to talk about how we can achieve the first 2 objectives using I-nteract. I'm going to discuss how the consumer A non-expert user can generate a customized 3D model using I-nteract, and how a designer can test the design 3D model in response to the physical world stimuli prior to manufacturing. All the objectives mentioned before can be achieved by a system that can enable real-time interaction with both virtual and the physical world simultaneously. And this is where I-nteract comes in to develop the interconnection between the cyber and the physical worlds with human in the loop. So, I-nteract is a visio-haptic mixed reality system that lies at the frontiers of mixed reality, artificial intelligence, human-machine interaction, robotics, machine learning, dynamics, and control. I-nteract provides visual feedback using mixed reality glasses and force feedback using haptic gloves to enable interaction with the visual objects in three-dimensional physical space. This video shows a user interacting with a virtual object using I-nteract. The misalignment between the hand and the virtual object is caused due to the incorrect depth perception by a single RGB camera by which video is recorded. However, in reality, the experience through the HoloLens depicts much better alignment between the user hand and the virtual object. Now I'm going to talk about some use cases that demonstrate how I-nteract can enable a non-technical consumer to generate customized 3D models for 3D printing. I-nteract provides a novel scanning method to generate a 3D model of a physical object by estimating its contours using a haptic glove. Traditional text scanning techniques require either scanners or physical objects to move around each other. Therefore, the developed scanning strategy is suitable for the scanning of the physical objects which have restrictive movements. An example of such a situation is a patient with a fractured bone. We have implemented this strategy to 3D print a customized orthopedic cast for a human forearm. The user takes the measurements of the arm using the haptic glove. By fitting the virtual cylinders onto the arm segments, based on the measurements, a mesh is generated between the two consecutive virtual cylinders, estimating the shape of the arm. Resulting into the generation of a customized 3D printed orthopedic cast. The next video demonstrates how a CAD can be enabled in mixed reality using I-nteract. Constructive solid geometry allows the user to construct complex 3D models by using Boolean set operations, such as union, difference, or intersection on simple building blocks like cubes, cylinders, and spheres. Using a constructive solid geometry, the user is generating a 3D model of a chair from primitive shapes out of the thin air. The virtual buttons can also be accessed by the voice commands via HoloLens. Generating a complicated 3D model from scratch is laborious, even using an immersive interface as shown before. Therefore, to automate the 3D model generation, we have integrated the I-nteract with a deep neural network. Using HoloLens, the users take an image of a desired physical object. The captured image is sent to the cloud to be accessed by a laptop, where a deep neural network generates a 3D model based on the image using single view mesh reconstruction. The 3D model generated from the deep neural network is uploaded back to the cloud to be accessed by the HoloLens and display the user in mixed reality. The image shows a 3D model of an office chair generated using deep neural network and displayed to user in mixed reality. This video demonstrates how I-nteract enables the user to adjust the dimensions of a virtual object with respect to design constraint in the physical workspace. The image shows the 3D model of an office chair generated using deep neural network based on single image resized with respect to the 3D printed dimensions, and on the left side, the black chair is its 3D print. Now I'm going to present some use cases to demonstrate how I-nteract enables the designer to generate a digital twin and enables real-time testing of a design 3D model prior to manufacturing. I-nteract can not only capture the shape of a physical object, but can estimate the elasticity of a deformable object as well. Spring constitute a basic building block to estimate and simulate the elasticity or stiffness of a deformable object. In the image, the user is interacting with a physical spring to generate its digital twin. The force applied by the user is measured by a force sensor, and the displacement in result of the applied force is recorded by a glove position sensor to estimate elasticity. The force feedback for simulating the estimated elasticity is controlled by a neural network-based approach. Finally, to illustrate how I-nteract can enable the interaction between the physical and virtual objects to improve the design process for additive manufacturing, I would like to present a use case of designing spring for a shock absorber. A simple shock absorber comprises an inner cylinder and an outer cylinder and a spring. To design the 3D model of a spring of a specific spring rate for the given real and uh, inner and outer cylinders, the user can measure the dimension of the outer cylinder part to get the spring's internal diameter and the desired free length of the spring between the two cylinders using haptic glove by a method similar used for generating orthopedic cast. Based on these measurements, I-nteract will generate 3D model for a desired stiffness. After the generation of the 3D model, the user can interact with both the physical parts and the virtual spring simultaneously. Interact using I-nteract to measure the stiffness of the generated virtual model to validate the design prior to the manufacturing or 3D printing. The work presented has been extracted from publications shown on the slide. I would like to refer you to these papers for further details. Thank you for inviting me to interact. Please feel free to ask any question.
Thank you very much, Amar. It is nice, very nice. Like, so you have, you can start from a photo and then generate a 3D model from this deep deep network, and then be able to edit it using interactions, right? So I think that is a big thing. So so how does the deep network work then? So it takes the image and then generates a 3D model and parameterize that, and then you interact with the parameters directly, uh, and then it go through the another network again, or the
Yeah,
network is recursive, or is it just
yeah. So for the time being, so the biggest challenge in uh, integrating the deep network with the HoloLens and the other components of Interact is that the computation of a neural network. So
yeah,
the complicated the neural network is, the difficult it would be to integrate with the system and to get a real-time output inference from the neural network.
yeah,
So the neural network, so this design approach is based on a generative design approach,
mhm,
which is kind the idea that in which very similar to our objective, that to automate the engineering design constraints or the other complicated stuff, uh, while only taking basic commands from the user, like in this case from an image, like an image. So the neural network that we used is soft rasterization. It's a generative neural network.
okay,
You might have heard a type of a GAN neural
yeah, yeah,
network,
yeah,
and it is not recursive, but it's a generative. You give it an
okay,
image, and it will generate a whole 3D model for you.
right, okay, okay, that's nice.
Yeah.
So I mean, it's surprising how you can take a 2D image and then map it to a 3D object. Uh,
Yeah, yeah. So yeah, it's a very challenging problem, and
yeah.
it's also very currently a very hot topic of research as well. The
Mm,
one I used is one of the top soft rasterization neural network technique for generation of single mesh reconstruction. However, I am also currently improving the neural network uh, uh,
mm,
right now. It's in process, but the integration with the system strategy will remain the same, and it's more like you present a neural network a lot of 3D models, a mapping between a 2D image and the 3D model, and the neural network is going to generate a similar, not exact, but a
yeah,
similar
yeah,
3D model.
okay,
The advantage would be in the future could be the latent interpolation, that I will take the images of two chairs, which and I can design a chair that resembles the in interpolation of both chairs.
I see. That's
Yeah,
great.
so that there are
Excellent.
many research areas that could be
Right.
explored in it.
Jacob has a question.
Yeah.
Jacob?
Hi. Thanks for the presentation. It's really cool. Quick question on the neural network output side. Because obviously, if your input is an image and output a 3D model, does it only generate the points, or you also, because in your case, it seems like you also get the connectivity and the faces of your 3D model. Is that the case, or do you generate the connectivity between the vertices differently?
That you're talking about, that there are different formats to represent the 3D model.
Yeah.
The most famous is the STL, that is also used for additive manufacturing. So ultimately, the output of my 3D model would be an STL file. But
Mm,
the thing is that the HoloLens accept an OBJ format, and there is not much different in both of these formats. If I have an obj file, I can easily convert into STL file, so it gives me a complete 3D model. And if in mentioned in the paper, if you look into the soft rasterization method, what it does, that it takes a sphere and it deforms into a 3D model that you require based on the 2D image. So the output that we are getting is an OBJ format, the whole 3D model that you can print.
Right. Okay. Yeah. So you're always are you always deforming from a sphere to make the sphere match the shape then?
Yeah,
That's the case. Okay.
but that is dependent on the type of the neural network you would use.
Yeah.
But
Okay. Yeah.
the ultimate objective to get in our project is to get an STL file so that we can 3D print it.
Yeah. Got it. Thank you.
So because I can understand why you asked the question, because there are several neural networks that only generate vertices of a 3D model. And
Yeah.
yeah, I can understand it, and that is very difficult to generate faces out of them. So that's why the selection of neural network is very important, that give you a complete 3D model. And now the research is much advanced that will generate a whole 3D model for you.
Yeah. That's pretty cool. Yeah. Thanks.
Any other questions? So Amar, is it like how sensitive is this for shadows? Like, so I can see in the original chair picture, the lighting conditions and the shadows, are they ignored or are they taken as features by the network?
So the biggest challenge in training a neural network is to obtain a data set. So the data set is the most time consuming process for any neural network application. So the data set that is usually used in the research is ShapeNet, which is a very ideal data set in which they get the 2D images of a 3D model. Like they get the 2D images from different angles of a 3D model and then train the neural network.
Mm.
For that, like that condition, the image has to be ha- ideal in that sense to generate a 3D model using such type of network. So what I did basically is that I took an image from HoloLens that is from the real environment.
Mm.
Then I sent it to the uh, an online background removal API that is
I
also
see.
another neural network that is trained to remove the background and
Mhm.
extract the information about the chair from it is. So in such kind of data set, it's very important that you pre-process the image uh,
Mm.
before sending into a neural network. But the future work will be concentrated on using a data set that will provide you natural images, and then you can directly train the neural network to avoid this step of extra uh, background removal.
Mm. Mhm. Um, yeah, that's great. So you said the user get haptic feedback, right?
Mm-hmm.
So this is 3D printed. Okay, that spring, and then at finger level you get that stiffness. But how does the network know the mechanical properties of the object, like the chair? So because it just got a picture, right? Does it compare with known libraries in the background, or?
So the interaction with the deformable object is
Mhm.
somewhat different from generating a 3D model from an image. So in this example shown in the slide, in this use study case, um, we implemented uh, an hardware that can detect stiffness of a physical object,
Mhm.
deformable physical object, by interaction. Like, for example, I will compress the spring
Mm.
multiple times, and the force sensors data and the position sensor data will be recorded, and the elasticity will be estimated based on that. So this digital twin generation is not image based; it's
Mm.
purely an interaction based by the haptic club. The
I see. I
dimensions,
see.
yeah. So the idea is that to extend this idea, the idea is basically that you can model any deformable object, any elastic material, with the help of the mass spring model.
Yeah,
So if you can do that for a single spring, then you can estimate the elasticity of a more complicated object. And the future direction is to use multiple fingers simultaneously
right.
to achieve that for a complicated object in this
That's
scenario.
that's wonderful. Yeah. So that then it can be like more user centric, right? So it is like, the same object will have different haptic feedback for different people depending on the gender, their age, and things like that, right? For example, a teenager who is exploring the same object will feel a different stiffness than, uh, maybe a girl or a boy might have different. So it is, then the design becomes more user centric. Is it the purpose?
It can be that way, but to have a constant parameter for everyone,
Hmm.
uh, it would be like it could that is a very nice use case, but in this scenario the objective is to get the actual parameter from the physical object.
Mm,
So if I am interacting with a physical object, if some other an old person is interacting with a physical object, so there is a phase of calibration before
mm,
that, a very simple step of calibration in which the size of the hand and the force feedback by different user is
mhm,
taken into account. And the neural network shown in this loop is
mm,
specifically designed for this purpose, that the user will train a neural has to interact with the neural network to train it first by interacting with it, and
mm.
then train it according to his own specific features.
Okay, okay. Thank you. Yeah. So, last question I have. Um, a lot of people complain that, wearing a HoloLens for a long time is a more like, distraction, or sometimes get dizzy, or it is not possible to wear for a long time, right? So the roughly maximum time span is about 20 minutes, and then after that they don't like it.
With the uh, with with the improvement in the technology,
Mm,
the size of these technologies is going to be compact with the passage of time. Even if you see the haptic glove is much portable and lightweight as compared to the previous haptic gloves, or even the recent haptic gloves that exist in the market.
mm, mm.
So
Yeah,
yeah,
this is
so
this is one reason, like, for, let's say, this intuitive surgical systems like, minimal invasive surgery. It gives you depth perception, the console, and then the way they have designed it, like, so you just lean on it, your weight is on the thing, and then your hands are kind of pointing downwards then upwards, so you don't have to have, like, a lot of gravity compensation for a long time. A lot of these gloves, haptic gloves, I think still haven't addressed that problem that intuitive surgical has addressed effectively. Maybe these are things then, people you can even consider for future, right? So a console where somebody can lean on it, and then the weight is on the thing, and they are looking downwards than looking straight ahead, because in the HoloLens the direction doesn't matter, right? So you can be looking downwards and still you are seeing the thing, and then your hands, you don't have to compensate for gravity, they are just hanging. So I think those ergonomic side has to be little addressed in the future, for wider acceptance. And maybe those are things you can consider in the future, hopefully.
yeah, Interact also has a great potential to do the teleoperations as well. For the
Mhm.
time being, we were focused on the additive manufacturing area, but
Right.
definitely I think that Interact would provide. So you can, for a surgeon, you can give him haptic feedback for the instrument that he want to use, virtual instruments, and
Yeah.
somewhere in some other country or remotely there will be an actual machine that would uh, be controlled by the
Right.
interaction with that virtual model,
Hmm.
or with with the manipulation of the hand. So also with the interact, there has been research with the haptic glove. There was research going on that the haptic glove can also provide you the weight of the visual object as well, uh, because this haptic glove provides the kinesthetic feedback, that is a feedback that lets you feel the shape of the object and weight as well. So
Right.
yeah,
Yeah.
definitely it needed to be addressed these challenges when you are designing these kind of systems for tally operations.
Yeah. Certainly. But I think there's huge potential for this for surgical preparation. Now, you know what happens, like, so if there's a, especially in pediatric cardiac operations, and the day before the operation, the surgeons take a picture of the or scan of the heart of the child, because this heart is very small. They had to do the surgery, practice the surgery a couple of times before doing on the real patient. What they do is like they 3D print a heart of the same size of the child's heart, and then they do the surgery on this rubber heart a couple of times to reduce time to access the arteries and things like that. So we struggle with this kind of training, robot assisted training. So our focus is mostly how to get this robot assisted training to be very efficient. So your system is a very promising solution, I guess, because you can put a laparoscopic camera or an X-ray image, and then you can map that just 2D image of the heart, or let's say the organ, to a 3D soft object organ that can be 3D printed, and then you can feel it with this haptic glove. And then hopefully we can train the surgeon the day before on that, right? So what do you think about that? Do you think it is possible? Like, that image, that any improvement in that makes a huge difference in a child's kind of a, pediatric uh, operation. So we have this with the Guy's Hospital in London, and they do that regularly. And then all the surgeons we are collaborating with, they need to they need to have a model, hardware, physical model right next to them while doing the surgery, so they can touch and feel it and then make guesses. So what do you think about that?
Yeah, actually, the mixed reality or the haptic mixed reality, including the augmented glasses or the haptic glove, has huge potential in the educational field as well, to provide tutorials to the surgeons or to demonstrations
Mm,
as well, in which you generate virtual situations that are not that are very difficult to generate physically.
mm,
So that definitely exhibits a huge potential in the improvement in the surgery field as well. One such application, interesting application that I thought about when I was when I it's not very much similar, but it's very it's a medical based application. Like in one of my applications, I talked about how we can generate a customized uh, cast, orthopedic cast for a
mm,
broken bones.
mm,
So one of the idea I have, or I might do implement it in the future, is so I was thinking, so using such technology like scanning your arm to fit a customized cast. Along with that, we can also provide an augmented feedback of the broken bone, so that
mm.
not only the shape of the arm is taken into consideration, but also where it is, but the bone breaking point also can be considered while designing the cast. So yeah, so mixed reality possesses an immense potential in the area of medical as well.
Great, excellent. So I mean, if you're interested, I can introduce you to some of the surgeons we are working with in the future. So excellent talk, Amar. Thank you very much, and thank you very much for joining today to listen to this talk, everybody. You can unmute your mics and clap the speaker.
Thanks. Great. Well done, our Trish. Quick question, Trish. I know some of the undergraduates will be interested in this. For some reason, they can't attend because they have something else on at the moment.
Yeah.
Is there some way of making the video available so that?
Yeah, sure. I will download the file and share with you.
Yeah. I can link it then to my Blackboard page. Yeah. Thank you.
Right. Excellent. Thank you. Thank you very much, everybody.
Thank you
Thanks,
very
Amar.
much.
Well done. Bye-bye.
Bye. Thank you.